Example problem 5.6, bone fracture estimation from page 169. Actually, it starts on 168 and continues on 169. And it reads as follows. A bicyclist is watching for traffic from the left while turning toward the right. A street sign hit by an earlier car accident is bent over the side of the road. The cyclist's head hits the pole holding the sign. Is there a significant chance that his skull will fracture? We are given no information really as far as any numbers. It's kind of an odd problem just because the author of the book had this happen to him, or one of the authors, so I wanted to throw this in. So later it says you have to estimate some stuff. It'd be nice to know this information. 70-kilogram cyclist moving 3 meters per second. And the skin indents during the collision as he makes contact with the pole with a stopping distance of 10 centimeters and an area of contact of 4 centimeters squared. So there's a lot of stuff that got left out that I've included. My initial picture is looking, pedaling his bike. By the way, these pictures are excellent. And the final picture, his face is in contact with the pole, and he's moved. The change in position is about 0.1 meters or 10 centimeters. Initially velocity is 3, and the final is 0. So if we model this situation with a impulse momentum graph or bar chart, we would start with, we've got our initial momentum of the bicyclist initially in the x direction. Then there's going to be an impulse provided on that bicyclist. Oh, I'm sorry. Let me say plus an impulse provided by the pole on the bicyclist in the x direction. It's going to be equal to the momentum of the bicyclist final in the x direction. So the bicyclist initially has a momentum. It's his mass times his velocity that we can represent with a bar. And at the end, we know that he's got no momentum. It brings him to a stop. Well, to get from this much to 0, your impulse would have to be equal to an opposite of that initial momentum. So I'll make a bar roughly the same size down. As I scroll down, we can represent these situations mathematically or algebraically. We've got the mass of the bicyclist times the velocity initially in the x direction plus the impulse, which is the force of the pole on the biker or bicyclist in the x direction multiplied by the final time minus the initial time, which is equal to the final momentum, mass of biker, velocity of that biker, final in the x direction. I should change this to, now I shouldn't do that, velocity of the biker initially in the x direction. We know that this person's velocity ends up being 0. And if that final velocity is 0, then this entire final momentum is 0. So, and we would want to get the force by itself. So I would subtract, I thought I picked red, mass of the biker, velocity of the biker initially in the x direction from both sides, That would cancel that here. So we've got force of the pole on the, I said bicyclist earlier, but biker is just easier to say. You can imagine a big burly guy with tattoos if you'd like. Final velocity minus initial velocity equals opposite mass of biker, velocity of biker initially in the x direction. We want to solve for the force. Divide by this, Tf minus Ti divided by Tf minus Ti. That cancels now. So we're left with the force of the pole on the biker in the x direction is equal to the opposite of mass of the biker, velocity of the biker initially in the x direction over the change in time, final minus initial. And this is another point where we've got this fun little equation called stopping time interval. Which is in the book but not on the equation sheet. And it is defined as Tf minus Ti is equal to 2 times x position final minus x position initial over final velocity x direction plus initial velocity in the x direction. We know that the final velocity in the x direction from up here is going to be equal to 0. So Tf minus Ti, which I still say you could do this just as easily, is equal to 2. Final position, since it moved 10 centimeters, is 0.1 meter minus 0 over 0 plus initial velocity 3 meters per second. That means our final minus initial times is 0.067 seconds. So that's the amount of time that force is being applied to create an impulse. Remembering what we had above, it was force of the pole on the biker in the x direction is equal to opposite of the mass of the biker, velocity of the biker initially in the x direction, over, change in time, Tf minus Ti. Now we have a numerical value for Tf minus Ti. We have the mass, we have the initial velocity. So this is going to be equal to negative 670, kilograms times 3 meters per second over 0.067 seconds, which gives us a final force of negative 3,000 newtons. Now, the question is there a significant chance that his skull will fracture? And there is a kind of a grisly measurement that is given to us in the reading that says that you need to have 17,000 newtons per centimeter squared to break bone, which sounds kind of messed up, but if you are in the business of testing helmets, testing airbags, seatbelts, this might be something you need to know. So we need to figure out, did it meet or exceed or not even get close to that number? Well, we need to do a force over an area. That force was 3,000 newtons, and whether it's negative or positive, in this case it really doesn't matter, over the area that this pole covered on the guy's head is 4 centimeters squared. This ends up being 800 newtons per centimeter squared, plus or minus doesn't really matter in this case. So was it enough to break his skull? No, probably just enough to ruin his day.